I'm Tommaso Poggio. I'm the director of CBMM, the Center for Brains, Minds and Machines. And I'm very happy to host today David Vogel, who is coming to speak to us about machine learning applications. David was an MIT student in the math department, and he got involved in prediction, first in healthcare and then in the world of hedge funds. He started a hedge fund less than 10 years ago, which is now a multi-billion dollar company. And is not only the founder, but also the chief scientist and mathematician. And I think machine learning is at the core of artificial intelligence, is at the core, in a sense, of science itself, because the paradigm of machine learning is the paradigm of modern science, being able from data to generate models that can make predictions. That's why astronomy is different from astrology. And that's why the challenge of finance is one of the biggest challenges you have, from past data to predict the future. And the test is pretty clear. Either you make money or lose money. And so it's very good to have David here, and he will tell you about some of the competition he has won over the years. There have been initially a few competition in prediction. There was many years ago one that the Santa Fe Institute organized, and more recently Netflix, and now there is a flood of them with, of course, the popularity and the importance, practical importance of machine learning. So David, I'm happy to welcome here.
Thanks. Thank you very much for having me. I guess first and foremost on the intro was that I am an MIT graduate, and it's just such an awesome place here, and it's just so great to be here. So I'm really happy to have been invited to give this talk. I'll give a little bit about my background. Some of it was mentioned. I have about 95% of my background is on the applied side. I have done a couple peer-reviewed publications on techniques, but almost all has been on the application side. I've done predictive models in a pretty big variety of areas, many professionally and some just on the side. I guess a lot of people in their spare time might enjoy golf, and some other people might enjoy fishing, and I enjoy analyzing data sets in my spare time. So you can see I've done everything from sports predictions to medical outcomes. In the process, I've actually developed a lot of predictive modeling software on my own, which is sort of unique to a lot of applied people because there are a lot of tools out there. But with that, although on one hand it sort of slows you down to split your time between application and creating the software tools, but having written the software tools also allows for tweaking algorithms to make them specific to certain applications, and you can get that little bit extra accuracy when you have that ability to tweak algorithms. So I have done quite a bit of software, of my own software for software. In terms of competitions, I've participated in a lot of them over the years. I'll be talking about a couple of them. One thing that I love about competitions, I encourage people to do them in general, is they're just a great learning experience. You can learn a lot from publications as well, but I've found that if a certain new method is published and it's compared to other methods, there's always a little bit of bias because the author would know that technique the best. And so in participating in these competitions, you can get an idea of a fair comparison of all these different algorithms from different places being pitted against each other. Currently, my 90% of my time is as CEO and chief scientist of Voloridge Investment Management. So people know me mostly now as a hedge fund manager, but really less than half of my career has been in the hedge fund space. And I really consider myself still more of a data scientist and able to apply algorithms in a lot of different areas. So I also, in 2014, started the Vogel Foundation and on the board of a couple nonprofit organizations. So a little background on the Voloridge firm. Being not from the finance industry, I didn't have buddies with $10 million to throw in the hedge fund, so we started actually with $80,000 under management. And over the years, as the returns started attracting more investors, we kept multiplying until suddenly, somehow, we got to where we're managing $1.5 billion. Probably most important of those bullets is that we got, since I'm here at MIT, we got 7 MIT alumni. We try and hire the best and brightest for our company, and certainly a a huge amount of talent here at MIT. Our investment strategy is is completely quantitative. We use machine learning-based models not only for the predicting directions of stocks and futures, but also for the risk management. And I'll talk a little bit about that later on in the presentation. And also, through the Vogel Foundation, we try and do some data-driven based decisions in terms of making a difference in the world. And climate change we've found to be probably the most challenging problem that needs a lot of scientific focus. So I'll start with just some conceptual overview of ensemble models. There was a great study a while back by Elder Research where 5 different modeling techniques were applied to 6 different data sets. And the y-axis is the accuracy of those models. It's actually error rate, so lower is actually better. And you can see how no one technique worked best on all the data sets. So you got, for example, neural networks did well on most data sets, but very poor on diabetes data, and logistic regression did well on diabetes, but poor on investment data set. So you have this problem with individual models where there's weaknesses of those models, and you have to try a lot of different things in general to find what works best for that particular data set. Now, this next slide shows if I were to ensemble or combine those models, you can see the error rate drop dramatically. So the probably the most basic version of ensembling is just a straight average of those models. And you can see that red line over here is just a straight average, dumb average of those modeling techniques, and even that performed better overall than any of the individual techniques. And there are some more intelligent ways to ensemble those models that performed even better than that. So with that concept in mind, 2 of the most popular used ensemble-based methods are bagging and boosting. I'll talk about those techniques, and then what I call miscellaneous is this group of sort of customizing an ensemble for a specific data set. There's really no generalizing on that. So the basis of these methods is a decision tree. A decision tree in its pure form is probably the least accurate of any modeling technique. And the reason why it's so discrete, you run out of dimensions very fast. If you had 1 million records in your data set and you split the tree 10 times, on average, you're going to have only 1,000 left in each node. So you end up not being able to use the value of all your predictors. So by itself, decision tree is a very poor modeling technique. But when you combine them, this was discovered in 2001 or at least published by Bryman. If you average a large set of trees, then all of a sudden, and you sort of create some variability in those models based on different subsets of records and different subsets of variables, If you combine those, similar to that ensemble concept I showed where the group of models performs better, the bag decision trees performs extremely well. And it's actually, of course, way, way more than a single decision tree, and it's actually more accurate than regression and neural networks on most problems. So this was published in 2001 by Leo Breiman, and I actually have since met other scientists who were using it before, but sort of kept it proprietary and didn't publish the result. Just kept it for their own edge. So to give you an idea of how many trees you need for the bagging to work, this example is from one of the competitions. Yahoo put on a competition on ranking search queries. They had 700 predictors and about 500,000 records. And if you ran a single decision tree, and actually just give a frame of reference, a neural network, the neural networks and regression models got an R-squared out of sample about 0.35 to 0.4. And so this single decision tree, as we expect, performs very poorly out of sample. The difference between training and testing shows that it's extremely overfit model. But as you start getting 10, 20, 30 models, you see the out of sample R-squared start increasing. And around 50 to 100, you're passing the accuracy of the neural network and regressions. And then once you get to 400 or 500, at some point, always these bagging models start leveling off, because at some point you're just getting redundant trees, average them together. But the more trees will never be worse, other than the processing power required to train and score them. Now, gradient boosting is the second of the two very popular methods of ensembling. And instead of creating separate trees in parallel, you create them serially, where a small decision tree is made, the error is taken from that decision tree model, and from the residuals, the second tree is made. The learning rate is applied to avoid overfitting. And this also is on par with the bag decision trees. And I would say in my experience, having just applied both of these models to many different data sets, about 75% of the time I can get a better result with GBMs, and then other 20-25% I get better result with the bagging. And it's just very hard. I haven't been able to sort of categorize what type of data set is better. I just try them both. But one thing about gradient boosting is if you have too many trees, it will overfit. So whereas gradient boost, the bagging is much easier to tune, and if you're new to ensembling, that's probably the first one to try to get a good result. Gradient boosting, your out-of-sample result will improve, and then it'll start to go down as you overfit. So it takes a little bit more experience to apply a GBM, but overall, it's a slightly favored method in my opinion. So this was published by Jerome Friedman in 1999. It seemed like it was around 2005 where I recall a lot of people were using it, where it started becoming accepted as a very popular technique. One interesting thing when people ask, what does GBM stand for? In the original publication, it was gradient boosting machines. And then in more modern software tools, they call it generalized boosting models, but as far as I know, they're the same thing. So if you call them GBMs, then you can't go wrong. I guess that's the key with GBM, because if you're doing them in parallel, then it becomes more of a random forest. So I suppose by definition of GBM, you're always applying them to the residuals. So with that, those basics on GBM, random forest, I'll talk a little bit about the Netflix competition, which even though 10 years ago, it seems like there's still a lot of interest, because it was probably the biggest, was the biggest competition in predictive modeling ever held, with the biggest prize, $1 million, and also the largest number of competitors. There were 41,000 teams entered. So that was a competition we did not win, but we did rank as high as 7th, which hopefully qualifies me to talk about it. Though we kind of figured out if on a normal research salary, it would have cost them $12 billion to hire all those 41,000 teams. And if I were to flip that around and divide the $1 million across the 41,000 teams, the average researcher was making less than 10 cents an hour. One thing I thought really neat about this competition, because it was so widespread, is it really truly evolved what were the best practices. And that's why I'm always a big fan of competition, double playing field for algorithms. What was the most published algorithm and what the Netflix team was using was shown very quickly to not be the best algorithm. So there were multiple techniques compared. These are just 5 of them. In the interest of time, I'm going to focus on just 2 of them. The highlighted ones, I'll talk about item-based collaborative filtering, because that was sort of the published, most accepted method in the industry. That's the method that everybody was trying to beat. And then matrix factorization, which is a more elegant numerical solution. I'll show the difference in accuracy. So just to give a little bit of background on the problem setting, we were provided with 100 million records, basically just a big 4-column data set with movie ID, user ID, rating, and the rating. And so if every user had rated every movie, you'd have 9 billion movie user combinations. So it ended up being about a 1% sparse matrix if you were to make a grid between movies and users. And very minimal other information was provided. Movie title, date it came out, so nothing too significant in terms of adding to the accuracy. So the idea of item-based collaborative filtering is you take all the movies, you have this big giant correlation of every movie together. So in this case, there were 324 million movie combinations. And the way you correlate one movie to the other would be, for example, if I were correlating Lord of the Rings 1 to Lord of the Rings 2, I would find all the users who rated both those movies, just run a straight correlation, and a particular combination would be something like 0.9. So generally, people who liked number 1 would like number 2. Similarly, the movie like The Hobbit would rank something like 0.85 to Lord of the Rings 2. A movie like Children of the Corn would rank about 0. So you had this similarity index, or similarity matrix based on correlation of the ratings. Then the scoring of the model would simply be a weighted average of the most similar movies. So if I now, let's say a person had watched Lord of the Rings 1, I wanted to predict their rating for Lord of the Rings 2. Because it's not similar, Children of the Corn would not be weighted in there. But I would look at their rating on The Hobbit, I'd look at the rating on Lord of the Rings 1, and maybe 20 or so other movies, and it would generate a prediction. So there's some bit of variability on how you weight based on correlation, but those methods in that family all basically follow this format. So now matrix factorization, and I wrote Fantasy World on top because I start out with a hypothetical just to get the concept. Let's pretend that for every movie and every genre, we had a rating. So let's say we start with this data set where, okay, Friday the 13th is listed. It's rated very high for scary, but almost 0 for action comedy. Then you got The Hangover, which is top ranked for comedy, but low in the other areas. Then you got The Matrix, which is ranked top for action, and negative or low for the other categories. So if you have, if you were to start out with that, you could then run a series of regressions on each individual person based on their ratings to calculate coefficients. So their B0 would sort of be the constant, their average rating overall. And B1 would be how that person likes scary movies, how the person likes action movies, how the person likes comedy movies. And so you'd have you could basically fill in the blanks pretty easily if you had the left side as your starting point. Prediction would simply, if a person, like let's say Bob, had a high rating for scary movies, his prediction naturally with this formula would be high for, I said scary movies for Friday the 13th. So the other hypothetical is, let's say we didn't have the matrix on the left, but for each person, we started with a set of weights. So we know that Bob likes scary movies. We know that Dave likes action movies. And we know that Monica hates scary movies and likes action and comedy somewhat. So once you have that matrix, you could similarly run a linear regression to generate the weights on the left. And you'd end up with the same exact formula for the prediction. It would just be the sum products of the characteristics of the movies times what that person has as preferences. So since in the real world, you don't start out with any weights, matrix factorization starts with small random numbers. And then you iterate regression one way or the other. So first, based on these random numbers, you do regression, generate these weights, and you run linear regression, generate those weights. And so what starts out as nonsensical numbers slowly iterates to where you have very meaningful coefficients for both the movies and the person. So you end up with this very elegant mathematical solution. And you've, in the process, created genre variables. This M1, M2, M3. I mean, in the real world, there's maybe 5 or 6 main genres, but you could actually go, mathematically, you can generate 40 or 50 genres and get an improved accuracy. So these numbers can really go out. So the result was a much higher accuracy, but it's very hard to quantify in terms of real world terms. So what I did is I just ran a cluster on the movie coefficients, just a basic k nearest neighbors. And I end up with, and I'm going to show just some of the clusters that just came out of this nothingness that started with random weights. So you got in this particular cluster, you end up with a concentration of action movies. Second cluster, you got a huge concentration of cartoons. And you've probably noticed some of the imperfections. That's mostly cartoons, but then you got some movies, Buffy the Vampire Slayer thrown in there. It doesn't mean that the math was wrong. It just means that the same people who like the Tigger movie ranked the Buffy the Vampire Slayer. So it still is actually predictive, even though it may not make a lot of human sense. Then you got this sector, and it's just neat that all this came from randomness. You got a whole bunch of TV series in this one sector. Got a pretty nice concentration of horses in this other sector. Then when you look graphically at the sectors, there's one that stands way out, so you could characterize this as a most different type of person who likes Dragon Ball. Probably the biggest outlier of the sectors in terms of characteristics. So just some of the results. The team, my team that I was on was the Ensemble experts. That was our team name. With just collaborative filtering methods, with traditional methods, we were able to beat the Netflix team by about 2 to 3%. Using matrix factorization models, we were able to beat the Netflix team by about up to 5%. Then by sort of blending 20 of all different kinds of models together, we were able to get as high as 7.07% improvement. So enough for the ground prize, but then when, of course, we saw what the winning teams did, they had blended over 200 models to hit that 10% threshold. And so they were able to walk away that. So we did about 1/10 of the work necessary to get 70% of the way there. Just another competition. This was one that I didn't participate in, but helped organize. So I got to see very detailed descriptions of what people did. This was a telemarketing data set, predicting churn, appetency, and upselling. I'll go into the problem space because I got a few other things to share. But interestingly, that my ranking, bagging, boosting, ranked third and second. And the first place team had done both bagging and boosting and included a bunch of stuff in there too. So this miscellaneous, a bunch of everything type of custom ensemble seems to work in many different fields. And it gives the ability to customize based on that particular data set. Heritage Health Prize. So having learned lessons from these other competitions, a bunch of everything, I was determined in this competition to just generate as many models as I possibly could and have a pretty big team that could help with that. So we had actually a very talented team of 7 people. There was a pretty big prize, so you could call it maybe the second biggest predictive modeling competition. We're predicting hospital outcomes, so basically hospitalizations. So we were given a set of historical variables. The idea was to use whatever algorithm you could and submit a number of days in the hospital for each person given to us. So we were given 3 years of data to download. And then, of course, the 4th year, the outcome was withheld, and that was for scoring. And so teams would make submissions based on what they believed the year 4 outcome would be in hospitalizations. So in the interest of having a lot of methods, there were actually 2 completely different ways we thought to put the data set together in preparation for the machine learning. So approach 1 was to create predictors based on year 1. Use year 2 as length of stay in the hospital as the dependent variable for training. And similarly, you could take year 2 information, create the predictors, and use your dependent variable year 3. So you could train the model based on that. And then when you score the final data set, you take your year 3 information, create your predictors, and generate year 4. That was approach 1. Approach 2 was take year 1 and year 2 information to create predictors and use that to train on the year 3 outcome. So you use 2 years of input to predict 1 year, and then you score on year 2, year 3 predictors to get a year 4 outcome. So there's a big advantage of each one. Approach 2 could have much richer predictors. You had a lot more information in the predictors, but only half as many records to train with. Approach 1 had twice as many records, but simpler predictors. So it was sort of a big question mark would perform better because of that trade-off. As it turned out, they performed pretty similarly, but had different enough results. We were able to ensemble the 2 approaches to get an overall higher accuracy. We combined with, originally our team had 3, we combined with 2 other teams who had similar accuracy to further the ensemble idea that if we had 3 models that were about the same accuracy and we blended it all together, we could get even higher accuracy. So the final combined solution had over 100 models go into it. It had several GBMs with different different parameters, several random forests, just everything under the sun that we could think of to sort of emulate what Netflix winners had done. And the result was we actually won this competition by pretty significant margin. You can see our error rate compared to the other vendors. So again, that supports the idea that just lots and lots of models thrown into something will really fine-tune the accuracy and getting better and better. All right, so I'll talk a little bit about financial models. I like to start with this graph. I've asked stock picking, chart pattern people, which stock do you think is the most likely to, which one would you invest in based on these charts if I didn't know what they were. And so you got like trend-based people who like this one, definitely trending upwards. And then you got like value type investors who actually like this bottom one because even though it's gone down, it looks like the down period is ending, and you can buy it cheaply. You don't want to buy something after it's gone up. So there's some disagreement. And then I'll reveal I actually randomly generated these graphs. So using normally distributed noise. Punchline is very, very tricky to model stocks, at least with your brain. So using machine learning and using a lot of data, basically let the data decide. Don't try to let your eyes fool you with the charts. Use machine learning algorithms. Not all. I mean, there's plenty of other methods to do it as well. Some quants, they come up with a preconceived notion of what might be a pattern, and they backtest it. But what is in common with quantitative strategies is adequate backtesting, so that you can see that those patterns that you found work over a variety of market conditions. So in terms of measuring success of a portfolio, I'll give sort of the most widely used ratio is the return divided by the risk. Certainly not the only measure, but what's convenient about it is risk is measured as the expected standard deviation. Therefore, the Sharpe ratio is analogous to a z-score. And the nice thing about that is it doesn't consider the fact, let's say I had an S&P portfolio that the S&P on average returned 7.7% over the last 50 years and 15% standard deviation. So the S&P has a Sharpe ratio of about 0.5. Now, if I were to just evaluate based on total returns, I could up 2 to 1 and get 15% return with 30% risk. So I haven't really done anything special. So just looking at pure return is not a good way to assess a portfolio. But the Sharpe ratio is a pretty good measure to factor in the risk. In terms of minimizing risk, so actually just one important point on this, there's certainly a limit that when you're doing predictive modeling, it's very hard to generate more return. So there's certainly a limit to where you can only predict stocks so well. And so you can actually do just as well on the Sharpe ratio by minimizing this risk. So I think it's an important portfolio management tool to use machine learning or predictive models in the risk management. And so this is some of the ideas, like some of the risk management models that we integrate. We predict individual volatility risks. So for example, a company like Walmart is much less volatile than Tesla. So we could therefore have a bigger position in our portfolio to have comparable risk and better overall Sharpe ratio. Sector diversification. You can use published GICS sectors, but I'll show a diagram where we actually correlate every stock to each other and create analytical sectors. Zero beta, that beta is a measure of how correlated you are to the overall market. So minimizing exposure to the market in case there's a big crash, say like in 2000 or 2008, where the market dropped 50%, you don't want that huge risk in your portfolio. And liquidity-based measures, there's actually, as the fund gets bigger and you're trading bigger positions, there is substantial risk of influencing prices as you trade. So that's just a visual on our correlation matrix, where lines represent the thicker the line, the higher the correlation of all the tickers in our universe. That allows you to partition into sectors, which I found some interesting flaws in the published GICS sectors by doing this. One example would be, well, for example, gold stocks are very, very highly correlated to each other, and they should actually be in one sector. But retail stocks are, there's a lot not correlated to each other. For example, auto retail versus apparel, they don't correlate at all to each other, but a GICS sector might put them all together in the same risk management. Another interesting one I've found is Brazilian companies. Brazilian banks correlate more to Brazilian oil companies than they do to US banks. So even though they're in banks, it's that volatility of the Brazilian currency that is really driving the risk, the exposure to those markets. So doing everything analytically, I've found to be substantial in lowering exposure to sectors. And finally, there's the beta groups, predicting correlation to the S&P by ticker. You can figure out your overall exposure and balance better. So beta is a measure of how much a stock will move relative to what the market moves. So beta, if a stock has a beta of 2, if the market moves 1% up, you'd expect that stock on average to move up 2%. Likewise, a beta of 0.5, you'd expect it to move half of what the market does. And so I can see this red line represents betas of approximately 2. The red line represents a perfect prediction, and the dots represent the actuals of what we observed over this 9-year period. And one thing important to note is at the very high market moves, this x-axis being the market move, when the market moves 8%, these beta 2s don't move 16%, they move 13%. So there's this regression to the mean of a beta that's very important in the risk management, because you don't want to be market neutral one day and then not market neutral the day the market crashes. So very important to understand some of the nonlinearity of predicting beta of a stock. So my final application, I had to throw this out there because through the Vogel Foundation, we do a lot of work to try to fight against global warming. This is glacier data. So the ice samples that were drilled down. It's interesting, you can drill down and get an ice sample, and glaciologists can pinpoint pretty accurately what time it's from based on the decay of the beryllium and other chemicals in there. They can tell what the CO2 content was at that period in time due to the air bubbles trapped in the ice. And they can actually know pretty accurately what the average air temperature was in that region based on the density of the water. So you have this correlation of 90% between carbon dioxide and temperature, and the importance of this, and the reason why we've gotten more into this, is that we're currently, over the last 100 years, have pumped 150 parts per million CO2 into the atmosphere, and so there's sort of the question whether we're headed for a temperature, like the top graph or the bottom graph. So that's sort of the open-ended one, yet to figure out application going on, data analysis standpoint. So I guess with that, I'll happy to answer any questions.